So, as I told you that we'll be starting a new topic, CPU scheduling. And if we see the execution phases of any operating system or any system, so it would be like this, that for some time CPU would be working, or CPU is actually executing some programs, and some point of time CPU would be idle. So why CPU has to be idle? Because the processes might be busy in IO operation, and in comparison to CPU, IO operations and IO devices are very slow. So there would be CPU burst and IO burst. So in time, if we visualize the operation of any system, you'll find that there would be some CPU burst which are going to be interrupted. CPU burst are going to be interrupted by IO burst, and then again CPU, IO, and so on. So CPU would be in two states. CPU is working or CPU is idle. Now there are two types of processes in general. The IO bound processes, where there is a small burst of CPU activity and then they are waiting for IO, means it's more of IO. For example, our word processors, where you are typing and you are editing the document, or so you are more in an IO mode and a very little of CPU is needed. So these are known as IO bound process, where percentage of IO is more in comparison to CPU. There would be CPU bound processes where there is hardly any IO activity. For example, your simulations, your compilers, and they require CPU more often than not. So they don't need IO. So in general, based on how much CPU is needed by certain process, we can roughly divide or categorize them in two types: the IO bound processes and CPU bound processes. Now, there is a interesting process, and that's a operating system process. It is not a user process. That's a system process. I told you that operating system generally executes on a behalf of a process, user process. But there are certain processes which are operating system's own processes, and one of that processes, just a minute. And one of that process is that CPU scheduler. Now, what is happening, as we have discussed in our introduction lecture, that nowadays we have time sharing system. So every process gets a time quanta of execution, and then there is a timer interrupt, say every 100 millisecond. So running process need to leave the CPU, and a new process will get a chance to execute on CPU. So when this CPU scheduler is going to execute, scheduler process is going to execute when a timer interrupt occurs.
Sir, you are muted, sir.
कब से mute हूँ मैं?
Sir, just last 10 seconds.
Last 10 seconds. Somebody has done this. Okay, no problem. So okay, I thought you people are grown up. Anyway, so I'm repeating it. What is CPU scheduler? CPU scheduler is a process uh, which comes into, it's a operating system's own process, which comes into picture when you need to stop a running process, take it out of CPU, and then schedule another process. So in time sharing system, the timer interrupt comes after every time quanta. So you need to pick another runnable process and schedule it on CPU. Or if a process is going for any IO, then that process would be blocked, and scheduler can then remove that process from CPU and pick and choose another process for execution. Now this keeps on happening. This keeps on happening in any system, that scheduler actually becomes the most important process, because this process has to execute every time when any process needs to run on CPU. So between the execution of any two processes, you will find that CPU scheduler is executing. It's operating system's own process. Now, what are the design issues for fixing a scheduling policy? Now, you are going to decide which process should run next. So your scheduling policy should be minimizing the waiting time, average waiting time of all the process. Process should, if they are ready to execute. So there is a rider that if they are ready to execute, they must not wait for long in ready queue. Maximize CPU utilization. CPU should not be left idle for much time. So if there are processes ready to execute, your duty is to load CPU as much as possible. Maximize the throughput. Complete as many processes as possible per unit time. And this is most important, response time. Even if a process is not able to execute completely, but system should give some response that, okay, to user or to the user of operating system or user of system, that okay, process has started execution. Maybe it is not complete, but some response should come from the system. Minimize response time. Fairness. Give each process a fair share of CPU. This should not happen that some processes are executing continuously and some processes are getting starved. So these are the design issues for scheduling policies. So let's begin with a very simple scheduling policy, that is first come, first serve. So all these scheduling policies are in some manner or another are getting utilized in modern scheduler processes, and we'll be seeing these scheduling policy separately in isolation, but finally when we see the Linux scheduling, we'll be combining all these scheduling policy, and that we'll be seeing later, maybe in the next lecture. Process gets the CPU as they come or as they request for CPU. It is non-preemptive. Processes continues till their CPU burst is there. Means if CPU burst is of 10 seconds, just taking a hypothetical example, and if process has started executing on CPU, so for those 10 seconds, no other process can come and interrupt that, and that's why it is known as non-preemptive. First come, first serve, the process which is coming first will get the CPU first. Now, suppose in this example, if we see here, there are 4 processes, they arrived at the same time, and their CPU burst time is 7, 4, 2, and 5. And if we want to find out the average waiting time or average response time, so there is a technique known as Gantt chart, and using that Gantt chart, you can calculate all these values. So suppose we say that we we schedule the process in this order P1, P2, P3 and P4 because all have arrived at the same time. So P1 executes for 7 time units, then P2 executes for 4, then P3 executes for 2 and P4 executes for 5. If I ask you about the average waiting time and average response time, these are easy to calculate now using this Gantt chart. So P2 started at 7, so it has waited for 7 unit time. P3 started at 7 plus 4, 11. P4 started at 7 plus 4 plus 2, 13. So in this way, we can find out the average waiting time and average response time and so on. What would the average waiting time? P1 waited 0, P2 waited 7 plus 0 plus 7 plus 11 plus 13. So you add up and divide by 4, you'll get the average waiting time. What is the average response time? So in this case, the average response time is same as average waiting time. So as and when you get the CPU and you start execution, you'll get response from the system. Now, if I ask you a question, what is average turnaround time? Anybody can answer? Average turnaround time. So P1 is finishing at 7, P2 is finishing at 11, P3 is finishing at 13, and P4 is finishing at 13 plus 5, 18. So in this way, you can add up all these value and you can get the average turnaround time. What are the pros and cons of FCFS? It's a simple policy. It's fair also because every process will eventually run unless there is a big process and it captures the CPU entirely. Now, the important issue here is the waiting time depends on arrival order. Short process may stuck waiting for long process to complete. Suppose there is a long process having a large CPU bus time arrives first. So it will start executing, and because it's a non-preemptive mechanism, so short process may have to wait for a longer time. If you reverse the order, in this example only, if we reverse the order, because P1 is the longest process, if we suppose reverse the order and we schedule it like P3, then P2, then P4, and P1, fine, because all are arrived at the same time. Suppose we give CPU to P3 first, then P2 first, then P4 first, and then finally P1. You'll find that average waiting time is reduced. So this is the shortcoming of first come first serve scheduling, where waiting time depends on the arrival order. There's another mechanism known as another scheduling policy known as shortest job first. Associate with each process length of its next CPU burst. Just to avoid that particular effect we have discussed just now, associate with each process length of its next CPU burst. If you somehow can know the length of next CPU burst, and use these lengths to schedule the process with the shortest point. So the process which is having lowest CPU burst would be scheduled first. So you are giving a bit of priority here that the process which are having less CPU burst time would be having priority over the process which are having more CPU time. Now in this there can be two schemes. Non-preemptive, that once you give the CPU to process, it cannot be preempted until completes its CPU burst. Other is preemptive. Suppose you have at time 0 you have a process with CPU burst of 7 unit. After say 2 unit of time, another process comes which is having CPU burst of say 2 units. So remaining time of the first process is 5 and remaining time or the CPU burst time of the arriving process is 2. So now this arriving process can preempt, can stop the executing process throughout of CPU and execute itself. This is known as preemptive version of shortest job first. If a new process arrives with CPU burst length less than remaining type of current executing process, then you can preempt the currently executing process. And in some text, you may find that preemptive shortest job first is also termed as shortest remaining time first scheduling. Shortest remaining time first scheduling. So this is good in theory, good to study it in theory, but it is not practical because it is very difficult to predict the future. How can you predict the next CPU burst of the processes? That is difficult. So let's take example of non-preemptive SJF, shortest job first. So these are the process arrival time. So at 00 P1 was there. It is a non-preemptive version. CPU burst time 7. So on Gantt chart, P1 will be scheduled 7. Now P2 will come 4. No, what is the next shortest? Next shortest is because up till 7 time units, you can see all the process are there in the ready queue. They have arrived because P2 arrived at 2, P3 arrived at 4, P4 arrived at 5, and at 7 time unit all the processes are there. Now you can pick and choose. So next will be P3 because it is having shortest CPU burst. P3 will be scheduled. Then P2 will be scheduled. So P2 and P4 are having equal time. You can schedule either of them. So there is no issue. You can schedule either of them, or you can go for FCFS because P2 has arrived before P4, so you give chance to P2. Now, if you want to find out the average waiting time for P1, the average waiting time is 0. For P3, the waiting time is 7 minus P3 arrived. For P3, the waiting time is 7 minus 4 because P3 arrived at 4 time unit. So actual waiting is 7 minus 4, that is 3. Now for P2, 8 minus 2, that is 6. And for P4, 12 minus 5, that is 7. So average waiting time can be calculated in this manner. Now if you go for SJF, which is preemptive or shortest remaining time first, SRTF, if we run the example, you can see that P1 arrived at 00, so P1 will be scheduled. At 2 time unit, P2 arrived. The remaining time of P1 is 5 and P2's time is 4, so you will give P2 chance. So P2 will execute. At 4 time unit, P3 arrived. Remaining time of P2 is 2. P3 is having 1, so you'll give P3 a chance. So after P3 gets over. Now what is remaining? At 5 time unit, because P4 is also there. So P4 has 4, P2 has 2, and P1 has 5 at 5 time unit. So you'll get P2, give it to P2, then P4, then P1. And in this way, now how to calculate the waiting time? You see, When the process is finishing, go for that block. So P1 is finishing at this block. So waiting time of P1 will be calculated like 11 minus 2 because P1 has already started execution. So actual waiting time of P1 would be 11 minus 2. Waiting time for P2, where P2 is finishing in which block? In this block P2 is finishing. So it would be 5 minus 2. It would be P2 is finishing here 5, and how much it has waited?
Sir,
Minus
minus 4.
2 and minus
4.
2. Fine. So 5 minus 2 and it arrived at 2. So 5 minus 2 means 1. If you go for P3 finished here. 4 minus 4, it is 0. Go for P4 finished here. So P4 didn't get chance. So 7 minus 5, 2. In this way, you can calculate the average waiting time for SRTF. Any questions from anybody at this point of time? Any questions from anybody? So these are easy stuff. There's nothing here. Now, this is what is getting utilized in most of the modern operating system known as round robin scheduling, where each process gets a small time unit of CPU time that is known as time quanta. After this time has elapsed, the process is preemptive. A timer interrupt will come and the process will be added to the end of a ready queue. So let me switch to my whiteboard and let me explain this. So if there is a ready queue and from this ready queue, the process are getting supplied to CPU. So suppose process P1, P2, P3, and P4 are there. So P1 will be scheduled. After certain time quanta, there would be a timer interrupt. So running process will be taken off, and this running process will go into the end of the queue P1, and P2 will be scheduled. So in this way, in a round robin fashion, the process is happening. So this is termed as round robin scheduling. If there are n process in ready queue and the time quanta is q, then each process gets 1 by nth of the CPU time in chunks of at most q time units at once. So in this way, no process is going to wait more than n minus 1 q time units. So this is good for the response time because you know that in ready queue there are some 10 processes. Each process will get time in smaller chunks and will be able to provide time, CPU time to all the process in a rather fair manner. Maybe the scheduling itself is a difficult because it would be more number of interrupts and so on and so forth. More number of switching would be there, more number of context switching would be there. If you keep on giving interrupt after some time quanta, but in this way you can provide a fair sharing of CPU time among all the process, and that's why these type of systems are known as multitasking or time sharing kind of system where this round robin type of scheduling is there. Now, if you keep on increasing your time quanta, if time quanta is too large, then this round robin scheduling will end up towards FIFO or FCFS. If time quanta is too small, it should not be smaller than the time it takes to context switch a process. Otherwise, what will happen? Your scheduler process itself will get interrupted. Otherwise, overhead would be too high. So there is a trade-off that how much time quanta should we give for round robin scheduling, and there are lots of studies done, and in real system you'll find that there are multi levels of queues, multi-level of ready queues, and each queue is having different time quanta depending upon the nature of the process. So we'll see those things later on. Suppose we take example of round robin scheduling with time quantum 20. So there is a process P1 with bus time 53, P2 with bus time 17, P3 with bus time 68, P4 with bus time 24. So P1 get a chance 20, then P2 for 20, then P3 for 20, then P4 for 20. P1 get a chance again 20. P2 is finished in first time quantum. P3 get chance, P4 get chance. Then P1, P3, P3 because P4 is finished. So it may have higher average turnaround time than SJ because process is going to complete later because everybody is getting smaller time quantum, but better response time. But here we have abstracted an important process which runs in between. If we want to show in the Gantt chart what is going to happen, let me switch to my whiteboard. What is going to happen? So between any two processes, suppose P1 and after P1, P2 is coming, and after P2, P3 is coming. So there is an important process which runs here. And this process is known as dispatcher or scheduler. So process switching is not a trivial task because you have to save the context of executing process, save, and then load the context of a new process. So who will do this thing? This is done by a process of operating system known as dispatcher or scheduler. So between any two processes, the scheduler process has to run. And scheduler is also a process, dispatcher is also a process. So everything which has to be done. So what is happening actually, there would be a switch from running process to scheduler. Then there would be a switch from scheduler to the next process. So in reality, there are two context switches. When you switch from P1 to P2, in reality, there are two context switches. One, when running process switches context with scheduler process, and another when scheduler process switches context with the new process which is going to execute next. So in between two processes, there is always a scheduler process which we have abstracted in our slides, and which we'll be seeing very soon when we discuss our XV6 operating system scheduling policies. Any doubts or any questions to anybody? And if anybody is feeling sleepy, please wake up, because this is one of the most important concept which, believe me, not many fellows know, that how actually operating system switches from one process to another process. So whatever I am telling, means in previous two lectures, the interrupt handling, the process creation, and then we created artificial context of a new process. And today we'll be seeing that how to switch between one process to another process. These are difficult concept and not many fellows know this. So please be very sure that you know about these things. Bridgen, any question?
Yes, sir.
Excuse me, sir.
Yeah.
Sir, how much time does dispatcher takes between the context
Yeah,
switching.
that is a question. And if you remember, I have highlighted this point in this slide. If your time quanta is too small in RR scheduling, fine. And so it may so happen your dispatcher is executing and it is interrupted by a timer interrupt. So you have to be sagacious enough to set the time. Now, how much time dispatcher takes? Dispatcher is a highest priority process because it's operating system process. So it is not going to wait because this particular, it is not going to wait in ready queue because the dispatcher process is a resultant of your timer interrupt. If a timer interrupt, look how the things are going to happen. So suppose we take the example of round robin scheduling. A process is executing, a timer interrupt comes. So now come back to the interrupt handling. So interrupt handling will be done, timer interrupt will be handled, and at the end of the interrupt, this timer interrupt handling, if you think properly, at the end of this timer interrupt handler, there would be a call to the scheduler. कि भाई मेरा काम खत्म. Now my work is done. I have interrupted a process. I have pinged a process that now your time is up. So timer interrupt will come and will interrupt the process. Now, how this interrupt is going to be handled, the resultant of timer interrupt is a new process has to come and execute. Next process, which is in the ready queue. If we take the example of round robin scheduling. So how that next process can come? So timer interrupt at the end would be calling this scheduler process. And this and all those things, the saving of trap frame and everything will happen. And now the scheduler process will do the switching. So how much time it takes, this is immaterial, but you should ask your question that how important this process is. This is the most important process of any operating system. Because wherever a process is running, even now you remember, now you, if you actually analyze why we have created an artificial context of a newly born process. I have highlighted and hammered this issue that day that a new process which hasn't run on CPU, why we are maintaining a artificial context? Because we want that new process should look like as if it has been switched off from the CPU. And hence we have a artificial context so that our scheduler process does not differentiate it's a new process or any other process which has already switched out. So just to maintain generality, you have done that particular thing. That new process also have this artificial context, so that there would be no problem for scheduler. Scheduler should not differentiate. This is new process or this is already existing process. So scheduler for new process would be different, or scheduler process for already existing process is different. No, nothing like that. Just what you have done that day, you have created an artificial context of a new process also, which has just born, never run on the CPU, but still it is having an artificial context. And now scheduler job is okay. It has just to save the context of the running process. And context, you know what's the general purpose register, program counter, and all those things which a running process has done on CPU. So it has to save the context of a running process somehow and switch to the context of the coming process. That's what time it takes is immaterial. You have to align other things according to the scheduler process, as I have highlighted on the slide. Got it, bacha?
Yes, sir.
Any other doubt or question?
सर जैसे सर हम लोग अगर FCFS इम्प्लीमेंट करते हैं तो इसमें जैसे इंटरप्ट आया टाइमर इंटरप्ट
FCFS में टाइमर इंटरप्ट का बात नहीं होगा.
मतलब अगर आता भी है तो दोबारा उसी को शेड्यूल कर देगा क्योंकि उसका बस खत्म नहीं
Because
हुआ
when you are having FCFS scheduling in force, there would be no timer interrupt because FCFS is non-preemptive. You take decision on another basis, no?
Yes, got that.
So there is no issue of timer interrupt. And as you know, Brijen, that there are multi-level of scheduling.
Yes, sir, multi-level.
So in when we are talking about FCFS, there would be no issue of timer. Okay.
Yes. Yes.
Any other doubt to anybody else? Okay, if there are no doubts, then be very vigilant how this XV6 is handling this. And let me open the code of XV6 also. Just give me 2 seconds. Let me open the code. Code is visible, Virjend?
Yes, sir. Yes, sir. It is visible
Okay.
now.
Okay. So, as you may recall that XV6 uses following process states, as we have seen that. And just for your recall, it is there in line number 2340. So let's see the line number 2340. Just a minute. 2350. So you can see here this line that these are the process states which are there in SV6. Unused, embryo, sleeping, runnable, running, and zombie. And PCBs, process control blocks or proc structures, are all stored in the P table array. So we have seen a P table, which is nothing but the list of all the proc structures, list of pointer of all the proc structures. So these things you must recall from the previous lecture. So two things, one is XV6 are having these process states and proc structures are stored in a P table array. Now there is a CPU scheduler program which are in pages 27 and 29, and it starts at line number 2752, which is an operating system routine. So 2752 752, and this is 2752 is the schedule process, and scheduler program is given in 2708. So this is, you can see, this is a operating system routine which is running in a infinite loop. So in infinite loop, what it is doing, it is obviously acquiring the lock for the P table, and it keeps on checking whether there is any runnable process or not. So when there is a need to switch, the scheduler process is a forever running process. You can see an infinite for loop is there. So it keeps on checking whether there is any runnable process, and if there is a runnable process, we can schedule it on CPU. That's what is the work of the scheduler process. And the scheduler process later on calls the process at 2752, that is SCHED process. Fine. So this is what is getting done by the scheduler process. It's a system process. Each CPU core starts a scheduler process, does some basic boot up activities, and calls the scheduler function at line number 2708 when machine boots. Loops in this function forever to find active process to run and context switching to run. So 274252 scheduler, and it calls the scheduler function, which is nothing but looping in this function, the scheduler process looping in this function forever, just to find the active process for the context switching. If you can see here, I have highlighted every core starts because if there are multi-core CPU, there would be many CPUs, and every CPU would be having its own scheduler process, not its own. Every CPU would be having have to use the scheduler process because there are 4 CPU. Then every CPU has to use this scheduler process. Scheduler process is one, but every CPU has to start this scheduler process. As you can see, all action on the list of process are protected by ptable.lock. We have seen this. So everything is protected by ptable.lock. Why it is necessary? Any process that wishes to change this data structure must hold the lock. Otherwise, what will happen? 2 CPU might find a process runnable and both may schedule them, causing one process to run at 2 places. So at a time, one CPU can have access to scheduler process. The access to the scheduler process is mutually exclusive. Otherwise, what will happen? It may so happen because everybody is running its own instance of scheduler process, all the CPU. They may pick and choose a single process and might run on 2 CPUs. So this should not happen, and that's why there is a lock mechanism. During a context switch, every process has a context structure on its stack. Remember, when we were discussing about proc structure, in proc structure, there were 3 pointers: pointer to kernel stack, pointer to trap frame, and pointer to context structure. That lecture I told you that this context structure will be utilized later, and today is the date when we are going to utilize that context structure. During a context switch, every process has a context structure on its stack. And that is structure you can see at line number 2343. Let me show you 2343. So this is context structure. You can see it's nothing but some registers. And this is one important thing, the program counter. So struct context, and in proc structure, there is a pointer to this context structure. So during context switch, every process has a context structure on its stack, has values of the CPU register that must be saved during context switch. And you can see that important is EIP, the program counter, and few other general purpose registers. Program counter and other some general purpose register. Fine. Next. Now to switch the CPU from current running process P1 to another process P2, registers, means P1 is currently executing, and you need to switch the CPU from current executing process P1 to another process P2. So registers of P1, the registers which are there in context structure, which are part of context structure I have shown you. Registers of P1, when P1 is executing, it is using those registers, program counter and other general purpose registers. So the values of those registers, the registers must be saved in the context structure on the processes stack. So process which is going out must save the register on its stack. Where on stack? On the context structure. And then next step is registers of P2 which is about to run are loaded. Means when P2 is about to run, so CPU registers will be loaded by the content of the context structure of the coming process, that is P2, which would have been saved in a similar manner when P2 switched out in past. So this keeps on happening. So a process leaves the CPU, it saves the context in the context structure which is there on the stack of the process. A process comes, it will load the CPU register with its context structure which is on the stack of the process. And that must have been saved when P2 first switched out. So this keeps on happening. There is a switch function which does the job of switching between two contexts. And there is a word of caution also, Brijen, for you also. Be very attentive,
Yes, sir.
okay?
Yes, sir.
Okay. So there are some small tricks which you need to be carefully observing. Otherwise, you will not be able to understand, okay? And everybody, this is for everybody. For Brijen, I'm telling because Brijen has to deal the lab class also later on. So please be with me, everybody, and pay attention. I'm urging you guys, please pay attention. Otherwise, you'll not be able to understand this. Okay? So there is a switch function at line number 2950, which does the job of switching between two contexts, from old one to the new one. Now, what I am trying to do here, just please be with me and let me explain what I am trying to do here, just to make the thing simple. What is happening? Suppose P1, sorry, suppose P1 is executing a timer interrupt arrives. So this interrupt would be handled. And we know how it is going to be handled. We have seen interrupt handling. Remember and recall the trap frame, all trap function, generic function, then trap handling function. Remember interrupt descriptor table, IRQ number. Remember all these things. So this is going to be done. And finally, in the trap handling function, there would be a call to this and this scheduler will choose new process and then it calls SWTCH function, switch function. So whatever is happening before this, before scheduler, this is already covered. Now where new process choose is okay, that is okay. But first of all, what is required to be done, P1 should switch to scheduler, because scheduler is also a process, system process. So एक बार here switch and then scheduler will switch to new process. So, and both things are same. So P1 is switching to a scheduler process and scheduler is switching to a new process. Both things are same. because this is going to happen in a repetitive manner. You can consider scheduler as process POS. So P1 is switching to POS and POS switching to P2 new process. This is what is going to happen. Please be with me. So switch function line number 2950 does the job of switching between the two contexts. So let's see 2950 first. Switch. See this switch function, it is having two arguments, struct context old and struct context new. Struct context old and struct context new. Means pointer to the context of old process, pointer to the context structure of old process, and pointer to the context structure of new process. This switch function is doing. And if you can see this switch function before it returns, it's all in assembly language. It's all in assembly. It's nothing a C program. So what switch function does the job of switching between two contexts from old one to new one. Suppose a scheduler finds a process to run and decides to context switch to it. So what we are trying to do, we are trying to tackle this case that scheduler has find a new process and now is trying to switch to new process. We are tackling this case. This case from P1 to scheduler is repetitive, no problem. So we are focusing on this case from scheduler to the new process. Suppose scheduler finds a process to run and decides to context switch to it, line number 2728. So let's go to the scheduler process 2728. So this is your scheduler process. I told you 2708. Looping, checking, fine. And now here it finds a new process which is runnable, and now it is trying to switch to the new process. So here scheduler is calling a switch function. It is passing the context of this CPU process. What is this? This is a CPU process, per CPU process scheduler. So this is the address of the context of the CPU process or the scheduler process, address to the context of the scheduler process, and this is pointer to the new process context. And that's why you have seen in switch the double pointer for this old context. That's why in switch function you found double pointer for this old context. So let's see the switch function, you will be clear. Switch function is 2950. See here, struct context old. अभी old process है कौन सी? We are taking this case from scheduler to the new process. So the old process is the scheduler process. So scheduler process का context का address pass किया. That's why it is double pointer, and new pointer का new process का context का pointer pass किया. So these are the two argument for the switch function. Call the switch function with two arguments, a pointer to the context structure of the scheduler itself, which has to be saved, a pointer to the context structure of the new process to run. Okay, एक को सेव करना है, schedulers context need to be saved and a new process context need to be restored. And where is the new context structure? It is available on the kernel stack of a new process, which has saved its context entirely like this when it was switched out in past. Okay, okay, Viren?
Yes, sir. Yes, sir. It is okay.
Okay. Now let's observe the code of the switch. Need to understand what is on the stack when this function starts. So switch has been called by the scheduler process. So remember callee register and caller register, caller save register and callee save registers. So let me switch to my whiteboard and please be with me. So what is happening? This scheduler function is calling the switch function with two arguments, pointer to old and pointer to new context structure. So what would be there in the stack of the scheduler process? So it would be a return address because finally switch function has to return here. So it would be the return address. Okay. What else? So need to understand what is on the stack when this function starts. Before calling switch, you need to push the return address. The top of the stack will have the return address from where switch was invoked. Below this return address would be two arguments. So below this return address would be two arguments, and right to left, remember what are these two arguments? The old context pointer and new context pointer. So what you have shift when you were calling this switch in assembly, the switch function, you'll be pushing the on the stack, top of the stack, new context, from right to left, old context, and then the return address. So right now the return at top of the stack pointer is pointing to the top of the stack, and top of the stack is having the return address because scheduler function has called the switch function. Okay. Now एक extra काम सबसे पहले is happening on switch. Just see here. What is happening in switch function? What you are doing? You are moving whatever is there on the top of the stack. Whatever is there in something is there in the stack to register EAX and EDX. So in switch function, the first two lines are moving the content, some content of the stack to EAX register and EDX register. Just see what you are moving. So what you are writing? You are writing move 4 into whatever is on the stack to EAX register and move 8 into in EDX register. So means top of the stack is here. Every entry is 4 byte. That's how modern architectures are there. So when you add 4 on top of the stack, you'll go below, because you know that stack move upwards, move from higher memory location to lower memory location. So when you move upward, you are actually decrementing the stack pointer. But when you want to move downwards, you have to increment. So because every entry is 4 byte, so you are adding 4 to the stack pointer, and whatever is the content at this point, is getting stored in EX, means pointer of the old context is getting stored on EAX. Pointer of the old context, pointer to the old context structure, old means scheduler context structure, is getting stored at EAX. If you add 8 to the stack pointer, if you add 8, 4 plus 4, you'll be moving to this location, and what you are doing, whatever is there in this location, means it is pointer to the new context structure is getting stored in EDX. This is what we are doing in the switch function. First step, you can see here. So function saves the old context pointer and the new context pointer into two registers. EAX has the old context pointer and EDX has the new context pointer. Any questions? Any questions from anybody? Abdul Ahmad Khan, please mute yourself. If there are any question, you can ask. Okay, no problem. So, okay. And now you save callie save register. Caller save register पहले सेव हुआ होगा, वो scheduler function. Here in this situation, scheduler is the caller function and switch is the callie function. So scheduler ने अपने caller save register क्या क्या सेव किए? Argument register सेव कर लिए, right to left, return address सेव कर लिया. अब कॉली सेव रजिस्टर, नेक्स्ट इज ये फंक्शन सेव करेगा रजिस्टर को जो फंक्शन कॉल हुआ है. सो व्हाट इज गेटिंग सेव्ड बाय स्विच? EBP, EBX, ESI, EDI. EBP, EBX, ESI, EDI. ओके, EBP, EBX, ESI, EDI ये शिफ्ट कर देते हैं, पुश कर देते हैं स्टैक में. EBP और क्या क्या है? EBX, ESI, EDI. EBX, ESI, EDI, and your stack pointer will move here. Now this is the stack pointer. Okay. Now if you carefully see the context structure, so where was the context structure? Where is the context structure? On 2343. Let's see the context structure once more. So 2343. So what is there in the context? EDI, ESI, EBX, EBP. What is there on the top of the stack right now? EDI, ESI, EBX, EBP. And what is this return address? What is this return address? It is nothing but the EIP. It is nothing but the EIP, because when you have called switch function, the program counter was incremented to the next instruction, and this program counter is actually the return address. So it is nothing but EIP. So pointer to the old context यहां पे पड़ा हुआ था, क्योंकि फंक्शन कॉल हुआ था तो उसको डालना जरूरी था. पॉइंटर टू द न्यू कॉन्टेक्स्ट यहां पड़ा हुआ था, क्योंकि ये भी आर्गुमेंट था. रिटर्न एड्रेस टॉप ऑफ द स्टैक था, डालना जरूरी है, वो EIP हो गया. तो ये तो कर दिया सेव सब कुछ कॉलर ने. आफ्टरवर्ड्स स्विच फंक्शन ने क्या किया? ये 4 रजिस्टर सेव किए. ठीक, ये 4 रजिस्टर सेव किए, कॉली सेव. बट इफ यू सी केयरफुली, from EDI to return, from this point to this point in stack, actually this is nothing but context of scheduler process. पॉइंटर तो शिफ्ट कर दिया क्योंकि आर्गुमेंट था, लेकिन कॉन्टेक्स्ट तो अब बन रहा है ना बच्चा. दिस इज नथिंग बट द कॉन्टेक्स्ट ऑफ द शेड्यूलर प्रोसेस. जीवित रहिएगा सब लोग ध्यान से, बहुत इंपॉर्टेंट है. Now let's see the next piece of the code. Next piece of the code. Oh, switch function was where? (2950). Now what you are doing? You are doing move ESP EX and move EDX ESP. That's what you are doing. Move ESP EX and move EDX ESP. Let's write it first. Now what we are doing next is move ESP EX and move EDX ESP. So what you are doing, whatever is the stack pointer, whatever is the stack pointer, you are storing in the EAX register. And whatever is in the EDX register, you are storing in stack pointer register. मेरे साथ में रहिएगा. So what you are trying to do right now, EAX is having this address, old context pointer. Right now, EAX is having what? Whatever is the value, when we put bracket means at this address. So whatever is here 4 into ESP location, it is EAX means pointer to the old context. But pointer to the scheduler context is actually saved here, as we have seen from here to here. Means we have to store the current stack pointer to EAX. So current stack pointer would be stored in value at EAX. ब्रैकेट लगाया, जो भी इस एड्रेस पे होगा वहां सेव करना है. EAX के अंदर है क्या? ओल्ड कॉन्टेक्स्ट एड्रेस है. ठीक है, अब हमको क्या सेव करना है? इसकी जगह stack pointer. Means in simple term we are actually जो ओल्ड कॉन्टेक्स्ट का पॉइंटर यहां पड़ा हुआ था उसकी जगह अपन स्टैक पॉइंटर डाले दे रहे हैं, क्योंकि ओल्ड कॉन्टेक्स्ट का पॉइंटर डालना तो पड़ा शुरुआत में, क्योंकि फंक्शन कॉल हुआ था, बट ओल्ड कॉन्टेक्स्ट बना ही नहीं था. अब बना है ओल्ड कॉन्टेक्स्ट, तो ओल्ड कॉन्टेक्स्ट का पॉइंटर डालना पड़ेगा. यहां कुछ डमी पड़ा हुआ है, उस डमी को रिप्लेस करना पड़ेगा स्टैक पॉइंटर से. तो ये तो हो गया शेड्यूलर का ओल्ड कॉन्टेक्स्ट का पॉइंटर अब सही हो गया. किस लाइन से? इस लाइन से. अब क्या कर रहे हैं? अब अपन क्या कर रहे हैं? ईएसपी की वैल्यू चेंज कर दे रहे हैं. किससे? ईडीएक्स से. ईडीएक्स में क्या डाले थे? ईडीएक्स में डाले थे पॉइंटर टू द न्यू कॉन्टेक्स्ट. मतलब अब हम कहां जा रहे हैं? अब हम स्विच हो जा रहे हैं पॉइंटर टू द ओल्ड कॉन्टेक्स्ट. ओल्ड कॉन्टेक्स्ट कहीं सेव होगा P2 प्रोसेस में. इसका पॉइंटर पड़ा हुआ था यहां, जिसको हमने EDX में सेव किया था. अब EDX की वैल्यू किस में डाल रहे हैं? स्टैक पॉइंटर में. यानी स्टैक पॉइंटर यहां से उठेगा भाई और नई प्रोसेस के कर्नल स्टैक में कॉन्टेक्स्ट स्ट्रक्चर को पॉइंट करना शुरू कर देगा. जुगाड़. विजन भाई.
Yes, sir. Got the point.
हैं? समझ में आ
Yes,
गया?
sir. Yes, sir.
बच्चा लोग फाइन. Still operating on the stack of old process, need to move away. Function pushes some register onto its old stack. Whatever we are doing here, जो भी ये सब पुश कर रहे थे, ये अभी हम शेड्यूलर प्रोसेस के स्टैक में पुश कर रहे थे. Function pushes some register onto this old stack. Here only saving the callee save register, as I explained you. Caller save register would have been saved by the compile C code of the caller. Yes, like we have saved the return address and all. The register pushed by this code along with EIP return address pushed on the stack when the function call to switch was made, as I explained you, together will form a context structure on the stack. That's what I have explained. So return address, EIP and all these register together will form a context on the old stack. अब ये old stack पे process का context बना है. Fine. Next, after pushing the context onto the old stack, stack pointer still points to the top of the old stack. Stack pointer still points to the top of the old stack. So what we need to do? We need to, this top of the stack contains the context structure, true, as we have just seen. The pointer to the old context which was saved in EAX need to be updated to actually point to the saved context at the top of the stack. Remember this, why this must be done. EAX में जो old context का dummy pointer पड़ा हुआ था, तब तो context था ही नहीं. अब EX में हमको अपडेट करना पड़ेगा, अपडेटेड टू पॉइंट टू दिस सेव कॉन्टेक्स्ट at the top of the stack, line number 2969, and that's what I have done here, this thing. And finally what will happen? Finally, after saving the old context, stack pointer now shifts to point to the top of the stack of the new process. And this new context structure pointer was saved in EDX. And this value of EDX is moved to ESP. And that's what you have done. You have moved the value of EDX to ESP. अब ESP स्टैक पॉइंटर रजिस्टर में क्या हो गया? EDX की वैल्यू हो गई. EDX क्या था? ये एड्रेस था नई प्रोसेस के कर्नल स्टैक के कॉन्टेक्स्ट स्ट्रक्चर का. फाइन. The stack pointer has now switched from the stack of old process to that of new process, and a context switch has happened. खत्म. Any doubts? विजयन?
यस सर. सर ये जब ये नए प्रोसेस के स्टैक पे जा रहा है तो ये पुराने से नए पे जा कैसे रहा है?
स्टैक पॉइंटर एक ही है ना रजिस्टर हमारे पास.
ये सर एक रजिस्टर है.
उस रजिस्टर में हमने जादू कर दिया.
सर इस नए वाले का एड्रेस डाल दिया सर.
एड्रेस डाल दिया.
तो सर यहाँ पे क्या मेमोरी मैनेजमेंट भी आता है क्या? मतलब
नहीं, कुछ नहीं. स्टैक पॉइंटर तो एड्रेसिंग मोड ध्यान करो.
ये सर जैसे मतलब
स्टैक पॉइंटर हमेशा क्या दिखाएगा? टॉप ऑफ द स्टैक दिखाएगा.
टॉप ऑफ द स्टैक. ये सर
ये रूल है.
ये सर
ठीक. हमने पुराना जो टॉप ऑफ द स्टैक था, ठीक है,
ये सर
उसको सेव कर दिया EAX में, क्योंकि वो हमारा पुराने प्रोसेस का कॉन्टेक्स्ट स्ट्रक्चर था. तो हम लोग सेफ हो गए. ठीक. क्योंकि शेड्यूलर को दोबारा भी तो कभी रन होना होगा. ठीक है.
ये सर अभी इसके बाद दोबारा से आएगा,
दोबारा भी रन होना होगा. तो हम यहाँ आके सेव हो गए. ठीक.
ये सर
फिर हमने क्या किया? अब स्टैक पॉइंटर में कुछ भी करते रहो तुम, क्योंकि स्टैक पॉइंटर जो था वो हमने सेव कर लिया.
ये सर वो तो सेव कर लिया.
अब स्टैक पॉइंटर एक ही है पूरे सिस्टम में.
ओके.
स्टैक पॉइंटर 20 नहीं है. स्टैक पॉइंटर इज अ सिंगल रजिस्टर.
नहीं, जैसे सर हर एक प्रोसेस को एक पूरा वर्चुअल प्रोसेस एड्रेस स्पेस मिलता है, तो उनका अपना
लेकिन फिजिकली तो एक ही स्टैक पॉइंटर रजिस्टर है.
फिजिकली एक ही है सर. इसी वही मैं कह रहा था. तो जैसे वर्चुअल अलग अलग अगर है तो
वर्चुअल कुछ नहीं है. हमने उसी स्टैक पॉइंटर को कहीं और अपने प्रोसेस स्ट्रक्चर में, प्रॉक स्ट्रक्चर में डाल लिया. मेमोरी में, वर्चुअल मेमोरी में, हार्ड डिस्क में चला गया वो. ठीक है. वर्चुअलाइजेशन का मतलब ही यही है कि तुम फिजिकल रिसोर्स को मेमोरी और बफर्स में और डाटा स्ट्रक्चर में डाल के रख लो.
ये सर समझ.
अब क्या हुआ? अब जो नया कॉन्टेक्स्ट का पॉइंटर है उसको अगर अब हम स्टैक पॉइंटर में डाल दें
तो
हम कहां चले जाएंगे? स्टैक कहां पॉइंट करने लगेगा? स्टैक पॉइंटर
जहां पे पॉइंट कर रहा होगा,
जहां पे नई प्रोसेस का स्टैक होगा वहां पॉइंट करने लगेगा. यही हम चाहते हैं. हम पुरानी प्रोसेस की मेमोरी एड्रेस स्पेस से नई प्रोसेस की एड्रेस स्पेस जाना चाहते हैं. जब भी अपन जाएंगे शुरू कहां से होगा? टॉप ऑफ द स्टैक से शुरू होगा. तो हमको नया, हमें कॉन्टेक्स्ट उठाना ही है. टॉप ऑफ द स्टैक से कॉन्टेक्स्ट उठाना है, तो हमने स्टैक पॉइंटर चेंज कर दिया. टॉप ऑफ द स्टैक पे कॉन्टेक्स्ट स्ट्रक्चर है नई प्रोसेस का. अब देखो आगे स्विच क्या कर रहा है. आफ्टर स्विचिंग द स्टैक सब पॉप कर रहा है. हो गया. अब नई प्रोसेस में भी यही सब होगा. EDI पॉप होगा, ESY पॉप होगा, EBX पॉप होगा और EBP पॉप होगा. और उसके बाद नई प्रोसेस में भी क्या होगा? कहीं रिटर्न होगा या EIP होगा. और EIP चाहिए हमको. ये सब रजिस्टर पॉप होने के बाद EIP पॉप होगा. प्रोग्राम काउंटर भी भर गया, हम आ गए नए प्रोसेस में.
यस नया प्रोसेस में
हो गया?
यस
समझ में आ गया ना?
यस यस
हमने खाली स्टैक पॉइंटर में कर दिया जुगाड़।
वही सर मैं समझ रहा था कि जैसे दो अलग अलग प्रोसेस हो गए तो हम कहते हैं कि दो अलग अलग प्रोसेस एड्रेस स्पेस हो गया और दोनों प्रोसेस का जो मेमोरी लोकेशन है दोनों का सेम होता है। तो जब ESP में रखा तो इसीलिए मैं कह रहा हूं दूसरे प्रोसेस में गए कैसे, क्या मेमोरी मैनेजमेंट यूनिट का भी
ना
वो
कोई
आता है
मेमोरी
क्या?
मैनेजमेंट नहीं है। ESP केवल टॉप ऑफ द स्टैक बताता है, वो किस प्रोसेस का स्टैक है उससे कोई मतलब नहीं है।
अच्छा उसको पता ही नहीं है। ठीक है
उसको पता ही नहीं। ESP खाली बता रहा है कि कहाँ जाना है टॉप ऑफ द स्टैक, और तुम क्या कर रहे हो, तुम एक फंक्शन, तुम जा ही रहे हो, स्विच का मतलब ही है कहीं जाना है उसको, ठीक है। तो स्विच ने सब उसको पहले सब सेव कर लिया कॉन्टेक्स्ट, एक EX रजिस्टर में डाल दिया पॉइंटर भी, तो पुरानी मेमोरी में चला गया, पुरानी एड्रेस स्पेस में, उसका सब हमने सेव कर लिया कहाँ, प्रोसेस की एड्रेस स्पेस में, ठीक, पीसीबी में, कॉन्टेक्स्ट स्ट्रक्चर में चला गया। अब ये काम हमारा खत्म हो गया पुरानी प्रोसेस का, हम एकदम सेफ हैं, हम सेफ हैं। अब हमको कहाँ जाना है, हमको नई प्रोसेस में जाना है। नई प्रोसेस में कहाँ जाना है, हमको सब पॉप करना है स्टैक से। तो स्टैक पॉइंटर हमने चेंज कर दिया, नई प्रोसेस का कॉन्टेक्स्ट स्ट्रक्चर दे दिया। अब तुम जब सब पॉप करोगे तो आखिरी में क्या पॉप हो जाएगा, EIP पॉप हो जाएगा, तो प्रोग्राम काउंटर रजिस्टर भी पॉपुलेट हो गया। तो अब नई प्रोसेस वहीं से एग्जीक्यूट करना शुरू कर देगी जहां से उसने कभी छोड़ा था।
यस सर,
बात समझ में आ गया?
यस सर, यस सर, गॉट इट।
एनी अदर डाउट और क्वेश्चन टू एनी फ्रॉम एनीबॉडी? अभिज्ञान?
नो सर।
समझ में आ गया?
नहीं सर, थोड़ा थोड़ा मतलब मिसिंग है, 2-3 बार रिवाइज करना पड़ेगा।
मैं क्या, तुम लोग इतना तेज हो यार। एनीबॉडी एल्स? अमन, गॉट इट?
मतलब ठीक ठीक हो गया सर, अभी थोड़ा एक बार और देख लेंगे।